1.38, we're told, given this toolkit function f of x equals x squared, so the book is assuming you know that f of x equals x squared looks like this, and I'll highlight a few points here, because the way I like to apply my transformations is by moving these points and then drawing the curve. What I want you to do is graph g of x equals negative f of x, and h of x equals f of negative x. Okay, so in this case, I have a vertical, your book would call it a vertical reflection, a reflection over the x-axis. I prefer to think about it as just a special case of this guy right here. Playing the role of b is -1. That's all. So all I'm going to do is take all, well, this would be a vertical stretch, but really all that I care about is that I'm going to multiply all y values by -1. And as long as I'm here before I go graphing anything, I'll point out that over here I have something very similar, except now it's horizontal. I still call it a stretch, and I recognize that your book does not. But the reason I call it a stretch is because in my mind all there are shifts and stretches, and this is just a special stretch in that playing the role of b is -1. So when I say divide by b, divide all your x coordinates by b, you're going to be dividing all your x coordinates by -1. So let's go ahead and do that. You're like, this seems kind of weird. Why is he doing this problem again? We've done plenty that are a lot like this. There'll be kind of an interesting conclusion at the end, I guess. So let's do the vertical one first. So I guess this should be in red. This y value is 0. 0 times -1 is still 0. This stays here. This y value is 1. 1 times -1 is -1. So this guy would go down here. This y value is 4. 4 times -1 is -4. So -4 is here, this guy is here. And you do the same thing to the points on this side, and you end up with this graph right here, give or take. So nothing too special about this graph. This is just what it looks like. Fine, go ahead. Haven't gotten to my punchline yet. However, when I graph in green f of -x, something kind of interesting will happen. So for f of -x, I'm taking the blue graph and I'm dividing all the old x coordinates by -1. So this x coordinate was 0. 0 divided by -1 is still 0. This stays right here. This x coordinate was +1. +1 divided by -1 is -1. So I guess this would go over here. This x coordinate is 2. 2 divided by -1 is -2. So this goes over here. Whoa, weird. This x coordinate is -1. -1 divided by -1 is +1. This one goes over here. This one goes over here. What happens is when I'm drawing the graph in green, it's going to land right on top of the graph in blue. In fact, this right here is f of x and it's f of -x. It's the exact same graph. And then down here, this is negative f of x. So why is that so important? Well, really what it tells you is that this graph f of x equals x squared is an even function. Because f of, maybe I'll even write note, and I guess this will be in green, f of -x equals f of x. And you know what? This is overkill with the color coordination. But one time when I was teaching, someone did a course evaluation for me and they said I didn't use enough color. So now I go crazy with color. The green graph and the blue graph are the exact same. F of -x is equal to f of x. Anytime that happens, that tells you that f is an even function. That's important. If you go back to our little cheat sheet here, when we talked about even functions, you can tell if you have an even function in two different ways. Algebraically, it's when f of -x equals f of x. And geometrically, it's anytime our original graph is symmetric over the y-axis. So without even applying the transformations, I should have known that the graph in blue were an even function because it's symmetric over this y-axis right here. Anyway, maybe that's interesting. We're only talking about function transformations, but I get to talk about even and odd functions. Cool. It's a precursor to what will come next. All right, I'll stop.